In early 2018, natural language understanding was a fragmented engineering space. The dominant workflow relied on systems like Elmo and Word2Vec. Engineers used pre-training to generate contextual word embeddings, but they treated those embeddings strictly as frozen, static features. Because that base representation was locked, developers had to build bespoke, highly tangled architectures on top of it for every single new task they wanted to perform. The OpenAI GPT-1 paper proposed a different approach that eliminated the need for these task-specific architectures. GPT-1 utilized a task-agnostic design, one massive decoder block capped by a single linear head. Fine-tuning the whole model end-to-end allowed the network to adapt its internal representations directly to the target task. To understand the mechanics, we have to study GPT-1 as a linear data flow pipeline. Step 1 is the unsupervised pre-training of the transformer decoder engine. Step 2 is the minimal transfer trick, where we bolt on the task head and apply a fine-tuning objective. Step 3 requires input surgeries, forcing structured task data to fit into a linear decoder. By feeding data through this exact pipeline, the original GPT-1 model achieved state-of-the-art results on 9 distinct benchmarks. This 3-step data flow established the technical pattern used by modern large language models. Stage 1 is unsupervised pre-training. The setup is a standard 12-layer Vaswani decoder, trained over the massive unlabeled text of the BooksCorpus dataset. The mathematical goal of this stage is a standard autoregressive language model objective. This equation shows the model maximizing the log probability of each individual token, given the context window of the tokens that came immediately before it. Before data enters the transformer blocks, GPT-1 makes specific structural choices with its internal tensor math. The token embeddings and position embeddings are mathematically summed together rather than concatenated, and in a divergence from the original Vaswani transformer, GPT-1 abandons sinusoidal position embeddings in favor of learned position embeddings. Moving up to the output layer, the architecture utilizes a concept called weight tying. As you can see in this pipeline, the output softmax projection explicitly reuses the exact same input embedding matrix, known as WE. The structural choice reduces the overall parameter count of the model, while simultaneously acting as a stabilizing regularizer during training. This load-bearing generative stage forces the model to learn a deeply coherent latent representation of language, eliminating the need for downstream feature engineering. Stage 2 transfers that pre-trained engine to supervise downstream tasks. GPT-1 operates under a strict constraint. The massive 12-layer backbone must be reused identically. No new architectural wiring is permitted. The only structural addition is grabbing the final block's activation at the classification position and adding exactly one linear head, WY, on top. While the physical structure is reused, the entire network's weights are fine-tuned end-to-end. Only the WY layer contains completely new parameters. To train this new linear head, the model requires a fine-tuning objective, known as L2, but the equation reveals a subtle engineering trick. GPT-1 brings back the unsupervised L1 objective during fine-tuning, applying it as an auxiliary loss with a fixed lambda value of 0.5. The calculus supports this decision because the gradient decomposes cleanly. Functionally, this auxiliary loss acts as a regularizer to anneal the backbone. It prevents catastrophic forgetting. By using the unsupervised math as a stabilizer, the network stays tethered to its pre-trained manifold while it learns specific tasks. We still have a major structural bottleneck. A decoder expects one flat contiguous string of tokens, but downstream tasks like question answering are highly structured data pairs. GPT-1 solves this by moving the complexity out of the code and into the data. As shown in these tracks, it performs token surgeries using traversal-style input transforms. A unidirectional decoder has a severe left-to-right bias. Function AB does not equal function BA. Look at the similarity track. To fix this, the model runs both sequence orders simultaneously and then sums the resulting vector outputs together. This simple vector summation neutralizes the directional bias limitation inherent to autoregressive models. For multiple-choice QA, it's easy to assume the model generates an answer textually. It doesn't. It processes QA by creating one sequence for each candidate answer, and then runs a softmax classification over the entire set. Formatting inputs in this way proves that a single fixed network can solve diverse problems if the token layout is sufficiently flexible. Empirically, this three-step pipeline achieved state-of-the-art results on 9 of 12 benchmarks, including leaps in story close and COLA. But we have to isolate the underlying cause of the win. Was it the Vaswani transformer, the auxiliary loss trick, or the pre-training? Table 5 in the paper provides an ablation study to find out. This chart isolates the variables. Removing unsupervised pre-training caused an average accuracy collapse of 14.8%. Compare that to the architecture. The transformer only beat an older LSTM structure by 5.6%. And that auxiliary loss trick? The empirical data showed its average effect was scoring 75.0 versus 74.7. The ablation identifies unsupervised pre-training as the primary driver of these improvements, far outweighing the specific architecture or the auxiliary loss. The most historically significant finding in the GPT-1 paper was actually an unintentional byproduct: zero-shot emergence. As you can see in these rising curves, the model exhibited accurate task behavior simply by being conditioned with formatted text, with zero supervised fine-tuning loops. This phenomenon was the first published hint of prompting, executing a task by formatting the input rather than training ahead. This exact zero-shot behavior is the seed that GPT-2 and GPT-3 would eventually scale to extremes. GPT-1 codified the recipe: pre-train a decoder, fine-tune with one head, and format the input that governs the modern era of large language models.